Okay, let's go ahead and get started. So today we're going to learn a very simple yet very useful machine learning algorithm known as k-nearest neighbors. So k-nearest neighbors. Okay. Also called just k. Okay, so this is probably one of the most simple machine learning algorithms that we will learn. But in practice, it can be very useful. And as some of you know, I do consulting work and various programming tasks for a data science company. And more often than not, instead of using fancy neural nets or things like that, we will use something simple like k-nearest neighbors. Okay, so k-nearest neighbors is a classification algorithm. And it's very simple. So suppose we have two measures for our labeled data. And this is, again, this is supervised learning. Fix my camera. So suppose we have two features for our data, say x1 and x2. Okay. And we have our labeled data that appears, so maybe something like this, some blue data, and then we have some green data. And notice that this data is not necessarily linearly separable, right? In fact, it's not linearly separable. So we cannot find a line to cut this data into two pieces. But suppose that we have another data point that we want to consider, and it's like right here. Okay. Now k here is going to be some integer value. Okay. So maybe we say, okay, in our first example, we can take k to be, I don't know, 4. So what k-nearest neighbors does is it calculates using a metric or a distance, a measure, the k closest points to our point that we're considering. So in this picture, it might be like, okay, so this one looks pretty close, that one looks pretty close, that one looks pretty close, maybe like that one looks pretty close. Okay, so here, this new point, the 4 closest other points to this include 3 green points and 1 blue point. So with k is equal to 4, this point, I'll call it like p, p would be assigned to the label green. Okay. So how do we calculate this distance? Well, there's several ways to do this, but the most simple is just the Euclidean distance. So the distance between point 1 and point 2 is just, in this instance here, is just the square root of the difference. So this P1, I'll say X1. Actually, it's where the notation gets a little messy. So suppose we have two points x1 and x2. Then it'd be x11 minus x21 squared, right? And then x12 minus x plus x22 squared. So it's just the standard distance formula that you would learn in like a college algebra class. Okay. So the way that the algorithm is going to work is that when you when you consider a new point P, you calculate the distance from P to every other point in the data set, and then you assign it to the label of the K closest points to it. So I guess the best way to do this is just to illustrate the code, and then we'll talk about how to choose K after we program it and play around with it a little bit. So let me share my screen. Okay. Where's my, here. Okay, so for this example, we're going to again look at the iris data set. So we're going to use our data set. So using our data sets. We're also going to use plots. Pretty much every time you're going to use plots. And then we're also, at some point, or at the end of the lecture, we're going to need CSV for reading in a CSV file. Okay, so let's just load that. Okay, so let's go ahead and read in the iris data set. So iris is equal to data sets, and then the iris data set. Okay, and then we're going to have our X data, our measurements, be the array of X for X in zip, say iris dot sepal length, iris dot sepal width. And we're going to look at a third measurement here, iris dot petal length. So notice here that I'm looking at the entire data set now. I'm not cutting it off at 100. I'm going all the way to the 150th entry. Y data for the labels will be iris dot species. Okay. I equals. So we're looking at the entire data set. Okay. Let that run. It's going to be kind of slow at first. So again, just remember that zip here is just making, in this case, a triple, where the first entry is a sepal length measurement, second entry sepal width measurement, third entry petal length measurement. And we have labels Setosa, Virginica, and Versi color. So, for example, Y data of 60 should be a Versi color, right? And anything over 100 will be Virginica, anything less than 50 will be a Setosa. All right, so let's go ahead and plot this data and see what this looks like. So we're going to make a nice plot here by saying scatter, and we're going to say x-axis equals, what was it, sepal length. Y-axis equals sepal width. And then the z-axis would be petal length. Okay, and then we'll give it a title equals to, I don't know, iris data All right, so now let's overlay onto this. So scatter with an exclamation mark, and we'll look at text data from 1 to 50. And we know these are the Versailles color. And we're going to just give it a nice color with like white or something. Which you haven't seen me do that, but I like to choose my colors every once in a while. So now we just got to kind of repeat this process for the other points. Okay, so these will be, oh no, these are the first 50 are Setosa. The second 50 are the Versailles color. And then so this is color 1, 50, and the last 50 are Virginica. Here it should be 51. Versailles color, Virginica, and then we'll just change the colors here. Light yellow. Actually, let's see. We'll do like red or something, or green. Okay, let's see. So we make the plot, and then we overlay the first 50 points, and then we overlay the second 50, and then overlay the third 50. And again, the first time you run the plots, anything from plots, it's going to take a minute for it to run. Okay, so we see we have the Setosas, the Versailles color, and then the Virginica. So one reason why we didn't look at classification with the perceptron between Versailles color and Virginica was that, as you can see, they overlay with each other in a lot of ways. So they're not linearly separable. However, with k-nearest neighbors, we can still make accurate predictions. So first, we're going to need to define the Euclidean distance function. So function distance. So it's going to take points P1 and P2. It's going to return the square root of the sum of the array of differences. So this would be P1i minus P2i all squared for I equals 1 to the length of P1, for example. So the square root of the sum of the differences squared. That's what this is doing. Okay. So let's go ahead and test it out. So it's like a distance between, I don't know, x data 1 and x data 20. Right, so we have some measure of distance between them. Okay, so now that we've done this, we can write a function that will compute the k nearest neighbors, provided you give it k. So let's go and do that. So function KNN. Okay, so it's going to take a target point that you want to make a prediction on. We have our, let's just say, features, feature array. Then we can have something like our label array and a value for k. Okay, so I'm going to call this thing called a distance array, which is going to store all the distances from the target to the feature points. Okay, so this will be equal to, so I'm going to say, let's say the tuple or triple feature array I, label array I, and then the distance will go in the third entry. So distance from the target to feature array. Actually, feature array I. Move this over. Feature array I. Make sure my parentheses are good. Okay, and this is for I equals 1 to the length of the feature array. Okay. And then there's also another conditional if target not equal to feature array. Because we don't want to like include the target if it's already inside of the feature array. We can look at points other than itself. Okay. So I like to, there. So that looks okay. So that's my distance array. So what is this doing? So for each point in our X data, we store the point, we store the label of the point, and then in the third entry, we store the distance from the target that we're trying to look at to the point in question. And we do that for every single entry inside of the feature array or the X data. And so once we do this, we need to sort this so that the closer points appear at the beginning of distance array. So the way we can do that is by calling sort with an exclamation mark on the distance array. And we're going to sort this by the points, by the third entry in the point. So, this right here, almost forgot that. For those of you that are familiar with Python, this is like an anonymous function or something similar to a lambda function in Python. Okay. So sort with an exclamation mark is going to sort this thing according to the third entry in the array. Okay. Okay, and then you're going to return the distance array. But we're not going to return the whole thing. We're going to return from 1 up to k. Okay, because this is going to give us the k closest points. Okay. So let's go ahead and test this out. Where is that? Here? No. You didn't see where that. Oh, wait a minute. There's an extra. No, that's there. There. Oh. There's a comma there. Okay, so let's go ahead and test this out. So let's say k nearest neighbors of, let's say x data, I don't know, 30, right? So we know that's a setosa, and x data, y data, and let's choose k to be like 5. Okay, so we know that's a setosa, and we see that the 5 closest things to it are also setosa. Okay, so far so good. So we would like to predict that this point here would be a setosa, but one thing that's concerning at this point, or should be concerning to you, is that we have the labels for all of the data, right? We know what all the points are. But we need to be able to test this and make sure that we can find a k that works for points that we don't know. It's the whole point of machine learning, is to make predictions on data that's new, right? So one way that we can fix this is we're going to have to go back up here to the top cell and say something like, maybe instead of taking the all 50 of each of the labels, we can say from like 1 to 30, right? And then here we can say from 51 to 80 or something. And then here we can say from like 101 to like 130. Okay. So actually, let's make this 30 for each of them. Okay. So you see what I'm doing. I'm not taking all of the data, right? I'm looking at the first 30, and then first 30 from the other species, and the first 30 from the other species. So now I need to change my Y data. So how can I do this? It's going to take a little bit of playing around with, but we can say something like, all right, we can start by doing that. So that gets the first 30. And then for I equals 51 to 81, and y data comma iris dot species of I. This is kind of like a haphazard way of doing it. I'm just kind of trying to get the data split up right now. For I equals 101 to 131, it turns into y data iris dot species I. See if that works. Got an error here. In 10 and 2. So it looks like here, right here. All right, so we can figure this out. So I have a feeling it has to do with how long these things are. So that's what I'm checking. Kind of good to, you all get to see this. 30, okay. Just making sure that these have the same 51 through 81. That's the problem. I had it right the first time. There. So that should fix it. Oh. So pinned. Okay. So I also need to change these things here. And then I can just go in and say color, and here, okay. See if that fixes it. Okay, so that works there. So let me try this again. Yeah, there it is. I know what these are. So these are Setosa. So I can say Setosa. Where is the error here?
Professor, would you want to try push instead of append?
Oh, I have been programming Python lately. Thank you for doing that. There. Thank you. Okay, so so now we have we're looking at some of the data, not all of it. Okay, so let's run this again. So 1 to 30, 31, 60. I need to look at my X data to make sure I have the right dimensions on it. So oh, there's only 30 points in there. What am I doing? So 1 second here. Oh, I just made such a ridiculous mistake. All right, 1 second. This is very dumb that I just did that. I have to do this for each of the parts. I can't just all do it at once. Sorry about that. All right, so those are the first 30 measurements from the data set, and then for I equals, what is it, 51 to 80. Push into X data, virus dot sepal length I. So this will be a tuple here. Which, by the way, this is illustrating one of the processes which all of you are going to have to get used to with machine learning, and that's taking data and making it into test data and validation data. And that's what we're doing. All right, so that should push in there, and then for I equals 101 to 130, copy that there. There it is. So this is our incomplete data set. That took way longer than it should have, but it's important that we go through that process. Distance should still be the same. Don't need this cell anymore here. This still works. Okay. So, for example, now, so if we look at iris, so what point do we want to look at? So let's pick a point here. So P is going to be equal to the triple iris dot, what is it? Sepal length, sepal width, sepal length, iris dot sepal width. So we'll say like the 40th entry or something. Dot pedal length. All right, so this point is not in our training data. It's not in the data that we use to give it a label. So let's look at what happens when we put that in there. Pedal. There. Okay, so this point does not appear in here. Like we don't know, we don't know that this is a Satosin. But using the data that we do have, we get that it's predicted to be a Satosin. So let's look at another point. Like let's say like 140. Right? We don't know what that point is from the data that we have. We know from the data frame that it should be, let's see, it's likely a Virginica. Right? And that's true. That's the label that it would have. Right? So like, we can even like check here, like, dot species 140. Virginica. And we see that the majority of its neighbors are Virginica. Okay? Okay. So, I'm going to write a function to make a point here, so we don't have to type this over and over again. So, test point I equal to this. Okay. So let's go ahead and write out a nice little thing to test what that test point would be. So get rid of the cell here, and then say line and then line again, say target point P equal to say like test point, I don't know, 144 or something like that. And then say point line K equals to say 5 in this case. And then point line, a nice little dashed line. About that long. And then for I equals, I don't know, let's say we're going to call K nearest neighbors on this. So yeah. And point one. Eventually, this will all become a function. I'm just kind of typing it out right now. And then x data, y data, and k is equal to 5. For, let's say, I equals 1, length of test. And test has already been sorted. Line point, and then we can say I is equal to test I line point label equals to test I, and recall that if we look at the points, they're stored as like this, right? So actually, this should be a 1 there. This should be a 2 because that's the label. And then print line distance test I, and then the distance is the third entry there. Okay. Okay, and that. And then a nice little long line like that. Copy there. And some white space. Let's see what this looks like. So, oh, yeah, I never. Oh, it's a function. This would be 1.4. Not mean to do that. So 144. Okay, that's 30, line 2. Did I not run this? Oh, there it goes. Just I didn't run that cell. No, it's too jumbled up. Print line. Yeah, it looks better. Okay. So it sort of looks nice. This is like something you would present to like an employer or something. So maybe I want so the actual, so target label. And that's going to be species 1.4. So it has the label Virginica, and we see that the top 5 points tend to predict that it would be a Virginica. So I'm going to make this a function so I can play around with it a lot easier. So function show I. And you don't necessarily need to return anything, and I'm just going to place this by I. I'm also going to give the possible choice of K, I, and then everything else should be good. So that's so it's like a show neighbors. I don't know, like the 38th entry, and let's take K to be 4 or something. So we see that it's been labeled as Setosa, and this needs to be K. And the top 4 entries are also Setosa. Okay, so what about if we look at like 93 or something? It's predicted to be a Versailles color, and we see the top 4 Versailles colors. What about 99? Versailles color, Versailles color, Versailles color. What about one, say, 48? Virginica is what we would, is its actual label, and based off of the top 4 entries, this is what we would predict it to be. Okay. So I suppose that'll be it for today's lecture. Next lecture, we will continue looking at k-nearest neighbors and how to actually pick the right k for this data set. And then we will also look at that movie data set that I posted on Blackboard. Okay. So that, well, actually, I think we have time to make a nice little like visualization of this. No, we'll just we'll do that next time. This is good enough for today. Okay. So that will be it. Everyone stay safe, and we'll pick back up on Wednesday. I'll have a good day.